Good morning, students. Myself, Dr. Eustace Russell, working as Assistant Professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. Today, we are going to discuss the subject that is Robot Dynamics and Control. This subject is coming for the Department of Robotics and Automation under the semester of 6, regulation of 2021. Already, we seen one lecture video under various generalized coordinates we have seen in the last video lecture. Today we are going to see the remaining concept coming under unit 1. We will see one by one. So this is the syllabus. Already we have seen in the first video lecture of this unit 1, that is robot force models. Already we have covered generalized coordinates, generalized forces, and we have covered some of the basic concept also in that lecture video. Today we are going to see about static forces in manipulators. Static forces in manipulators. Followed by we will see some concepts oriented with that. We will see one by one. Static forces in manipulators. Before that, I want to tell what is static analysis. When a manipulator is required to exert a force or a movement on the environment, the end effector makes a contact with the environment and all joints remain static. The contact between the end effector and the environment results in interactive forces and movements at the end effector environmental interface. That is nothing but the end effector is the final output we are getting. That is only making a contact with the environment. That have a contact with the environment only. The contact between the end effector and the environment result in interactive forces. What are the forces that is acting over that? That will be results in the interactive forces and the movement also at the end effector. The static problem of the manipulator is to determine the relationship between the joint torque, that is force for prismatic joint, the torque for rotary joint. Whenever the robo we are having, prismatic joint will be there for attaining the linear motion, for rotary joint to attaining the rotary motion. And the force exerted by this environment on the end effect under static equilibrium condition. Various already we have noticed in the engineering mechanics subject under various equilibrium conditions you might have studied. For the system should be in equilibrium, what are the conditions should be maintained and what are the conditions should be satisfied. Then the next one is the force torque at each joint of the manipulator are transmitted through the arm linkages to the end effector, where the resultant force and the moment acts on the environment. So whatever the torque that is applied at the each joint of the manipulator transmitted through the arm linkages. So that will be transmitted to the linkages to the end effector. So in theory of machines also you might have studied that it's kinematics and dynamics of machinery, the 4-bar mechanism and slider bar crank chain mechanism. So whenever the input we are giving, that is transmitted to the next link and finally you are getting the output. The same thing you are getting in end effector. The manipulator carrying an object at its end point is equivalent to the object, is equivalent to the force applied to the end effector by the environmental contact as discussed above. In both the situations, the end point of the manipulator deflects by the magnitude determined by the stiffness of the manipulator. Only by the stiffness of the manipulator only we can determine that. Endpoint stiffness is an important characteristic of a manipulator that determines the accuracy of the manipulator and plays an important role in the control of mechanical interaction with the environment. So upcoming slide we will see one by one about that. So here this is the one diagram that is given for mentioning various links and movements and what are the torque that is applied over there and what are the forces that is applying. Here we can clearly see in the middle part of that link that is named as link I, and the previous link that is interconnected with that link I is link I minus 1. So that is transmitted to the next link that is called link I plus 1. So that is consider n degrees of freedom, that is DOF manipulator with the torque and force acting at each joint with determine the torque force to be exerted by the force actuators. To find the force and torque acting on each joint requires the force and movement balance for the individual links. That is link I with joint J. That is this one. Joint I only. and joined I plus 1. Joined I plus 1, that is coming the last part of the link, that is the right hand side. The connecting link, that is the previous one. The first link that is noticed, that is I minus 1. And the link I plus 1, that is the last end part of the link also. Then let us the vector f I minus 1, I denote the force that is acting on the link due to the link I minus 1. So what are the forces that is acting? Because of that only, that will be transmitted to link I, where the first subscript denotes the link exerting the force which act on the link of second subscript. The same thing we have noticed as f I plus 1. F I plus 1 means, so we are seeing that in the last link of that one. So minus means that is giving a motion in opposite direction, just like a spanner. If you are turning in one direction, if a person standing in the other side, if he is seeing or watching that spanner, it will look like it will moving in an opposite direction. So that also it is mentioned here. So another one thing important, for a link in static equilibrium, the vector sum of all movements acting on that arbitrary point is 0 only. For that we have a moment balance in that to consider that. Eta I minus 1 I O or I minus 1, then bracket of I minus 1 Ri plus I Ru I. These are the basic consideration we have took for that. The moment of the balance about the centroid we wrote there. Then what is Ri I minus 1 is a position vector from origin I O I minus 1 to origin O I. That is that one. Then these are the terms. What are the terms we have declared? That is mentioned over there at the equation numbers. Then the last equation 5.76 denotes the reaction force and movement from the environment to the manipulator. That is a final, the environment, how it is transmitted to the manipulator. We are going to see that. That is eta as well as the force that is applied. That is called endpoint force vector. It's also mentioned. The negative sign has been dropped as will be approximately taken when used in a force balance equations. The equation 5.77 showing that the torque to be exerted by the actuators, that is tau 1, tau 2, tau n upon T. Then what is tau I? Actuator force, actuator torque. If the joint is presbytic means we can show it, and revolute means torque should be considered that. Then based on that vector form we wrote that is tau I Ro I minus 1 I minus 1 z cap I minus 1 upon transfer matrix eta I minus 1 I. Similarly we wrote for next force also. Similarly what I wrote for the torque we are going to write for the force also. These slides give a glimpse about a Jacobian matrix, that is a derivation method, that is a split method, and well as interactive methods. That is the differentiation, the forward kinematics equation method 1, and the second one is the velocity propagation based to base equations. That is a method 2. The first one is purely of differentiation oriented. Second one is force and torque propagation as well as velocity propagation that tends to give the Jacobian matrix. So Jacobian velocity propagation, here we can see in this slide the executive expressions for the adjacent joint linear and angular velocity describe a relationship between joint angle rates and translational and rotational velocities. What is that means? I plus 1 omega I plus 1 equal to I plus 1 or I omega I plus, that is in the matrix form we wrote that 0 0 theta dot I plus 1, because that is the derivative part with respect to that is angular velocity with respect to time. That is the derivative part of that. Angular and linear velocities, here we can see the link of that one. Finally the end effector is there. You can see in the topmost side theta 3 link L3 L2 theta 2 L1, and it's have no angle corresponds to the first link. Just like that we can write as a matrix form, that is L2 S3 theta dot 2 L2 C3 plus L3 theta dot 2 plus L3 theta dot 3 followed by minus L2 minus L2 C2 minus L3 C23 theta dot 1. And finally, we will express the linear and angular velocity in the same base that we are differentiated in frame 0. Again, executive expressions for the adjacent joint linear and angular velocity defines the Jacobian in the end effector frame. That is, we can write like this. In the equation can be expanded. Here, the second line, nv equal to n d by dt x, which is equal to vx, vy, vz, omega x, omega y, omega z. That is in the Jacobian matrix. We wrote the multiplication of what are the distances should be taken into account. That is angular distance. What is that? When it is rotating means how much distance it is displayed. That is theta 1 dot, theta 2 dot, followed by the numbers. Here one we can see one example also. Given the known angle velocities with some arm configuration, some q and q dot it is given, and followed by the arm segment length li equal to 1. Then x comma y velocities of the end effector can be calculated by substituting in the system state at the current time into the equation for the Jacobian. Here we can see that minus sin pi by 4, minus sin pi by 4 plus 3 pi by 8, followed by minus sin pi by 4 plus 3 pi by 8. Above that matrix form we have the, it is written as Jacobian concept wise, Jacobian, that is j of q into q dot into distance will be multiplied that, and followed by the final step you are getting after simplification. You will get minus 0.8026 minus 0.01830 followed by 0, 0, 0, pi by 5. So these are the references which I took for preparing this content. Kindly go through the references. Thank you, students. Thank you for the kind attention. Today's for the first unit part 2 video is also over. Kindly go through it. Kindly subscribe the video and share to your friends. Thank you, students.